start. So my name is Graeme. I'm a paleontologist. It's been 2 months since my last paper. So this is work I've done with my colleague Lloy, who's been through the last 2 evolutions but hasn't made this one because he's been busy defending a thesis and preparing to move to a postdoc at the Smithsonian. So I like to finish my talks with conclusions, so I'm going to do my acknowledgements up front. So I'd like to thank the ARC and NESM for funding, and these people for helping with the construction and timescaling of the tree. So this talk is basically prompted by the question, what use are dinosaurs? So the cynical answer to this is dinosaurs are useful if you want to get your brand new fossil into the pages of Nature or Science, or the popular media. But I would argue actually there's one thing they're very useful for in terms of sort of a more objective approach, and that's paleobiogeography. There's a few reasons for this. First of all, with notable exceptions, dinosaurs are cursorial. This is why Jurassic Park was built on an island. But their fossil record spans the breakup of Pangaea, so from sort of an intact supercontinent to something approaching more like modern continental configuration. And also for fossil clade, we have a very good handle on phylogeny. Paleontologists love putting dinosaurs in trees. So there's a rich sort of history of discrete area approaches to biogeography. So this is an example from Nick Maskey's BioGeoBears package. I think he'll be talking about on Tuesday. But I decided to ignore all of that and try and focus my own continuous approach instead, and try and use something like the raw data we actually have. So the argument I'm going to make is that if we have some kind of supercontinent that we break apart into these sort of grey squares here, if we have endemism and vicariance dominating, we get sort of clade stranded on these different sections. And if we compare our geographic and phylogenetic distances, we find a positive correlation. If we don't break apart that continent with Brownian motion, sort of relatively fast pace, going on, something that I'm calling here passive dispersal, we'd expect to find no real correlation between our geographic and phylogenetic distance. And to complete this sort of picture, we could imagine a scenario where we get instead a negative correlation. And so this is where cis-detached are seeking to be as far away from each other as possible. So I want to test 3 hypotheses with my dinosaur data. So first of all, I'm going to suggest when Pangaea was intact, we ought to find there's sort of no obvious correlation between our geographic and phylogenetic distance. And as it breaks apart, we ought to move more towards positive correlation. But of course, not all dinosaurs are cursorial, so at some point birds evolved, and I'm going to hypothesize what would happen here is effectively a reversion to something more like the Pangaean world. If you're a bird, there are no barriers to dispersal, you can go anywhere. We ought to see instead this sort of non-correlation happening again. So in order to do this, we need some data. So I built what's the 3rd iteration of the dinosaur supertree, so sort of amalgamating a whole bunch of separate phylogenetic analyses together. This is what it looks like. You'll have some trouble reading the taxon names. But just to give you some idea about the way people are describing dinosaurs at the moment, there's about 1,000 species in here, which is more than the 2 previous iterations from 2002 and 2008 combined. So we need some temporal spatial data as well. Unfortunately, we have a good community effort in paleontology called the Paleobiology Database that basically gives us 100% coverage for all those species in the tree. So what do we get when we look at the results? So here we have a sort of timeline from where dinosaurs first appeared on the left around 230 million years ago to where the non-avian dinosaurs went extinct in the late Cretaceous, 66 million years ago. At the top here is some paleogeographic reconstructions of Pangaea slowly breaking apart. We have sort of the top here, we have our sort of endemism vicariance. In the middle we've got our passive dispersal, so no correlation. At the bottom we've got that negative active dispersal. So this is the results we get, and it's maybe not terribly consistent to everyone, but we can see our data sort of envelops that sort of zero line, that passive dispersal when Pangaea is intact, and it slowly seems to move more into that positive region of the endemism vicariance. So, but we also want to look at birds, so we can split our data in 2. So if we look at our non-avian dinosaurs, that basically follows the same trajectory because most dinosaurs are Mesozoic. So birds don't appear until the late Jurassic, so one potential candidate is Oronis, although recently this has been found to maybe not be a bird, and so perhaps the sort of more solid data point is Archaeopteryx in the late Jurassic. But we have a problem in that we don't really have a big enough sample size until we get to the early Cretaceous to do anything with birds, and here we find they actually fall out more in this sort of endemism vicariance area. So maybe this isn't surprising, because you evolve flight, you don't necessarily evolve the ability to cross oceans straight away. But we've also got to be cautious, and almost all of this data comes from exceptional preservation sites in China. And we see immediately after we lose that exceptional preservation again, we don't have a big enough sample. When we do have a broader sampling again in the late Cretaceous, though, we see that birds are separating from their non-avian relatives, but actually they seem to be moving more in towards this sort of negative region of this potential active dispersal. So I don't really know what's going on there, so I'm just going to move on. So that's all well and good in practice, but I've basically sort of told you a story based on some graphs. We don't know the true history with the fossil record. So what I want to do instead is basically build some simulations that we can throw the same kind of tests at, so when we know what the truth is, do we find the similar kind of results? So the questions here are, does simulated data match the empirical data? And there's a sort of secondary aim here that this could be used to create simulated data sets we could test discrete methods with. Well, I'm not going to talk about that today. So there's a couple of challenges when you're dealing with basically moving continents and organisms around on a sphere. So we know, for example, a date line is a periodic boundary condition. You can sort of pop out on the other side of the world when you cross it. And also the poles of singularities. So there's a couple of bigger ones that we had to overcome. So the first of these is what's called the point on a polygon problem. So here we need to basically move species around the polygon. We need to know if those moves are valid or not. So if you've gone into the sea or if you stayed on the land. So if I ask you here if that red circle is on South America, you will be able to say yes. But actually giving a computer a list of commands that make sure it knows how to do that is actually quite hard. This is called a point on a polygon problem. So the second issue is if we've got continents moving around the planet, we have to know whether or not they're colliding. So this is called collision detection, and every video game developer, this is like their nightmare, and here's an example where it's gone wrong. So these are basically a bit too hard for us to solve, so we kind of cheated a bit and we used circles. So everything's easier with circles. So, for example, our point on a polygon, we just say what's the great circle distance between our point and the center of the polygon. If it's bigger, it's fallen off the polygon, it's an invalid move. If it's less, it's on the polygon, it's fine. It's a valid move. So we can also look at collisions. So here we just want to look at the distance between the two centers. So it could be 2R, but we actually make this a bit more complex. We have this term we call squishiness, which is basically how much we allow things to overlap before we consider a collision to a recursion. And this obviously helps when we're dispersing between our continents. So we basically then have a model set up, and there's various inputs you can give this. So you can say how many continents you want, how fast you want them to move around, how big you want them to be. You can pick a starting configuration, something like a supercontinent, or you can have a starting configuration where they're all dispersed. You have another parameter called stickiness, which is how long they stay together before they rip apart. And then we have that squishiness that decides how much they can overlap. So we need inputs for our organisms as well. So at the moment underneath we have a simple constant rate first step model. We have the dispersal kernel, so how far you can move with each step. You have what direction you can move with each step, so there's a modified beta distribution, so you can set it uniform. Anywhere on the compass is equally likely, or you can sort of bias it to make east-west more likely or north-south. We also have a sweepstakes dispersal, or double dispersal in there, although that's kind of turned off in everything I'm going to show you. So this is basically built as an R package. It's still very rough. We only started building it in April, but if you want to go and look at it, you can go there. So just to give you an idea of what it looks like, this is not a very realistic run in terms of the parameters, but it helps visualize the data. So here we have basically a Mercator projection. Blue is the sea, green is the land. So we basically built a sort of Pangea here out of various circles, and we've got our clade start point there. And if we set it running, we can see basically we've got speciation, we've got dispersal, and you'll start to see those green circles break apart. and then basically underneath there is a tree, and we can sort of, at the end we can get to that and start testing things. So this goes on for a while. I'm not going to run it to the end, but I'm going to put my slides on SlideShare if you want to watch the whole thing. So we can then go back to these two hypotheses. So we can start with our Pangea. We can either break it apart to test this one, or keep it together to test this one. Unfortunately, I didn't get my results finished in time for evolution. Longer runs are still happening on my computer right now back in Australia. But the early initial runs, thank you, suggest that this is what we get when we simulate this, and this is what we get when we simulate this. So that's a bit of a relief for me. So obviously this is a very simple model, and what we want to do in the future is expand it, and there's lots of ways we can do this. First of all, we can't do anything with aquatic organisms or marine organisms at the moment. So the way you can do that is basically split our continent up into a shelf area and a land area. We could add ice caps, and we can have both of these be linked through to some kind of sea level function. We could also start adding something like climatic bands, and these could also affect the ability for organisms to disperse. And of course, what we really want to do is add something more realistic in terms of how we sample the fossil record, so we could set up sampling windows of differing temporal spatial extent. We could put some more topography in there when we have a continents colliding. What happens in real life is we build mountains, they could be barriers or impediments to dispersal. We could also, of course, have some kind of diversity dependence or species area relationship in there. So just to sort of sum up, in terms of having sort of an intact Pangea, we have this hypothesis about no correlation, and we seem to see that with both the empirical data with the dinosaurs and the simulations. Similarly, when Pangea breaks apart, or a supercontinent breaks apart, we get this positive correlation. Again, we can see that with our dinosaurs and with our simulated data. But the sort of bird hypothesis seems to sort of not pan out quite how I was expecting to, and there's still a bit of a question mark there about what's going on. And then finally, of course, our model basically needs to be more complex, so it's not very good. And that's where I'm going to stop now.
Well, we have plenty of time, 3 minutes for questions. If you would like to, yes, go ahead.
So, Graeme, so you're measuring this geographic distance and phylogenetic distance. What exactly are the inputs? Is it points, localities, or what?
So it's basically point data, yeah. So when I first showed this to John Alroy, it's like, why haven't your species got ranges? And that's partly because it's hard, but also because in terms of the fossil record, we're generally sampling, especially dinosaurs, mostly sampling points. So it's basically just paleo-coordinate data.
So it's a point somewhere with a fossil,
yeah,
right? And that has a distance to some other fossil?
Yes, it's just a pairwise distance between all of your species.
So is it like the center point of the species or the observed location of the species?
You mean if there are multiple occurrences?
Yeah, I guess. Yeah.
If it's multiple occurrences, we just put the mean at the moment. Yeah.
Oh, okay.
But most species, because it's dinosaurs, it's not a great fossil record, there is only one occurrence.
Anybody else?